And this company is Outpost Space. And I think Kelly first got the intro from Starburst to Outpost, right? And Outpost had heard, oh, we're a space company, and their name's Moonshots Capital. And we had done exactly 0 space investments prior to meeting Outpost. And so Kelly took the pitch on a Thursday with the leadership team and CEO Jason Dunn, who was a repeat founder in the space, sold his last company called Main Space, and texted me, did a double stomp on my head. I took the pitch the next day, and we had terms to them the next Monday. And so when we see a hot deal, we move like super fast, and that's the way we felt about Outpost. And so came time that we needed a VP of engineering, like kind of an important hire, and we just had a vacancy in leadership of the engineering, in our engineering leadership of the company. And Jason said, I have my eye on this guy, and I'm gonna go get him. And his name is Eric, and he's a mechanical engineering grad out of UCLA. He was with Boeing, he was with SpaceX, and he's with Virgin Orbit. And I said, you know, whatever you got to do, checkbook, option pool, go get Eric. And we were fortunate to land Eric, which made us very happy, especially as investors. So Eric, come on up here.
Slides? I think they're all loaded up there.
So I think AC, thank you, AC, for being here as well. He's one of the leaders of the team. So I'm going to do handoff to you. You got it. You'll take it from here.
Right on.
Thank you.
Quite the introduction. Hi, thanks for having me. So, as Craig said, Eric Wostenberg. I had the pleasure of joining Outpost last summer, and it's been an amazing experience thus far. Today, I wanted to share a little bit about Outpost, but more importantly, talk about engineering culture and what it takes for a small team to do incredible things. So I guess before we get into that, maybe I'll tell a little bit more about my background. I always wanted to work in space, and right out of college, I went to go work for a big aerospace defense contractor. But I was there for about a year, and it was a culture that didn't embrace risk. We were working on a small, tiny upgrade to a heavy lift rocket, and we're in Southern California. It was going to get made in Decatur, tested in Colorado, and flown out of the Cape. There was just such a disconnect between the engineers and what was getting made, and there wasn't really this appetite to make any sort of meaningful change. So after about a year of that, I had an opportunity to meet with a founder who had a startup 16 years ago, SpaceX, and I was immersed in a culture there that was doing incredible things. Very small team, young engineers, probably because we didn't know any better. We would try wild stuff. We'd design, build, and break, and then iterate over and over again. And so that's something for the last 16 years that I've had that I think is essential to any small team that's going to go solve hard problems. So we'll jump into a little bit about Outpost right now. So in the history of spaceflight, almost everything that we've sent up has been a one-way street. It goes up, it orbits around, it burns up on re-entry, and that's it. I think it's less than 2% of the mass that we've sent up to space has actually come back down. And so we at Outpost, we're trying to solve that. We're trying to open up the return lane. And right now, there's not a whole lot of good options. You have small capsules that can bring a couple kilograms, very small payload fraction, or you've got Dragon. I mean, SpaceX has effectively commoditized the ride to space. And so what we at Outpost are trying to do is build a platform that's scalable, that can bring up science, open up in-space manufacturing, do point-to-point delivery around the globe. It really is like a very flexible platform that scales nicely. So our solution is a bit unique. We have this big big folding umbrella structure on the front end. It uses a flexible thermal protection system that was developed by NASA over the mid-2000s. And the thing about this is it uses we come in on a ballistic reentry. So we're doing our deorbit burn. Well, first of all, we're in space, we're traveling at about 7.5 kilometers a second. And then on the far other side of the globe, we do a very, very small burn that just perturbs our orbit ever so slightly, such that we're hitting a spot on the other side of the globe. So if we're trying to land off the coast of Hawaii, we would do this burn over Northern Europe. So we're like, and so the issue that you have then is that there's all this atmosphere in the way, and it will perturb your orbit. So you're going to get this landing ellipse that could be up to 50, 60, 70 kilometers wide. And so this is where like the second piece of technology that Outpost is developing that allows us to have precision landing is the use of a autonomous paraglider. And what this allows us to do is come back in and deliver cargo within 5-meter precision. So that big heat shield I talked about earlier, what it does is it gives us a large drag area and a very low ballistic coefficient. And that's totally unique in that what we do is we go transonic, we go like below the speed of sound, very, very high in the atmosphere, versus a traditional capsule, which is coming in much quicker, much hotter, and you're not able to correct for that dispersion that we talked about from reentry. So this is pretty unique. Single surface paraglider we have on the left. This is like what you see people going out, like running off the tops of mountains and flying around. And it has a fantastic performance characteristic. So you have like 6 to 8 to 1 glide ratio. We can deploy them from super high altitude. And what's traditionally done is shown on the right, which is a ram air parafoil. And now I know this is like a little bit wonky, but the thing I'm trying to highlight is that using a paraglider is unique. They're not to be like designed to be deployed in free fall. And this is a super hard problem that we at Outpost have been tackling and made an incredible amount of progress on demonstrating its capability. So the history of airdrop started very early on. We had World War II, you're dropping round shoots out of airplanes, not a lot of precision. And then we moved to something that's shown in the bottom left corner there. That's the Army JPAD system. It's a robotically controlled ram air parafoil. They can be deployed at like 25,000 feet. They've got about 100 yards of precision. And what we at Outpost are trying to do is the next evolution of airdrop. And that's either using these high altitude paragliders to give us way more range or through space point-to-point delivery. So we started this presentation by talking a little bit about the engineering process. So what I wanted to dive in and share with you was this project we've been working on right now, which is building a prototype unit to demonstrate this autonomous paraglider landing. So these paragliders are not designed to do this. They're absolutely not designed to be deployed in free fall. It's really hard. There's a few guys that are kind of crazy, shown in the picture on the right. They'll like jump out of helicopters and try to do these, like throw these paragliders out behind them. And you see it come out and they're all tangled up and it's, I don't know, they're crazy guys. But we're effectively trying to do this autonomously. So what we set out to do was, over the course of 6 months, build a prototype, build a GNC control algorithm, uses GPS and IMU magnetometer to deploy this, control the paraglider, and then demonstrate its ability to autonomously navigate to a precision landing. So this is what the team came up with. This is the unit on the left. It uses 2 motors to control the brake lines on there. We have the deployment mechanism, the glider stored up on top. And then that image on the right there, we've been spending a lot of time up in the desert, dropping this from a helicopter and testing it out. So we get up there, and the team had built this over the course of 4 months or so. And we knew we needed to get some time on the water. So we put this video together. This is February 22nd. I think this is sort of important to note, like how quickly we're able to move through this development project. So we're up there. You can see it's dropping. It's falling under a drogue right now. It's cut away. We deploy our paraglider, and things do not go well. This is a pretty humbling experience for us. It's definitely not supposed to look like that. You see how there it broke in half. I will also note that I'm an engineer, not a film editor, so apologies for the low production value here. So we do this, we crater into the ground. The good news is they don't really care if you put holes in the desert, so we've put a lot of holes up there. And there we go. So, it wasn't, no. I will say, that article, it's bulletproof. We've dropped that thing now another 13 times. It's worked perfectly every single time. So, here's the robust test articles. So the team knew we needed to get back together. We needed to figure out a way that we can iterate on this quickly and cheaply. So what we did was we went back to basics and we started iterating on all the details of its packing and deployment. We started dropping from a crane, and you can see it still didn't go well at the beginning. But over the course of 4 different days, we just iterated and continually improved the process to the point where we were able to actually get this thing deployed and inflate consistently. A little bit better. Ooh. Yeah, that was almost a reportable incident there.
Ooh.
So you can see, the team was able to quickly come together, iterate the pack job, how we stow this thing, how we do the deployment, and we got to a point where we were quickly able to actually do this. So we were ready to go back up to the desert now and try it again into the helicopter. But the key thing that we need to note is there's no literature out there on how to analyze paragliders that are being deployed in free fall. There's no models, there's no tools. This is something that we had to go develop on our own. And so by instrumenting all of those drops, we were able to dimensionalize or non-dimensionalize the opening characteristics such that we could simulate what the loads were going to be and the opening dynamics under any sort of environment. So we're able to scale it, and from that crane data, demonstrate what it was going to be like under the helicopter. And then next month, we're going to go down to Tucson, and we're going to drop this from a high altitude weather balloon from 25 kilometers. And so we're going to use this data to extrapolate what that opening dynamics is going to be like when we get up there. So what you see here on this graph is data from our test flights. The dark colors are the actual collected data from the vehicle, and then it's overlaid on our model predictions. So not only was this useful in getting a reliable opening, but it gave us the ability to simulate this in all environments. So not only is this going to be a great tool for us on our orbital reentry and bring our spacecraft back to where we need it to be, but this can absolutely be used and scaled for larger cargos, for airdrop and precision landing. We're demonstrating right now 8-to-1 glide slope operating about 100 kilograms.
So Eric, if my mom were here, is my mom here?
You look great. We're very proud of you.
Again, satellite catches a ride on SpaceX or other, conducts mission long or short, redeploys to the atmosphere with the heat shield, and then the aha moment is the paraglide deploys. And it precision lands. Is Wynn Sheridan here?
Yeah.
And they could land it on a floaty in your pool. 5 meters, 5 meters, they can do this. So, and satellites, big and small, and they got more coming. But yeah, so this is tagline SpaceX, where Eric comes from. SpaceX of satellites, right? Returning satellites, and now you're getting like a look behind the curtain. And this has all been in like the last 90 days. All this testing that they've been doing.
Yeah, at the end of this, I'll show a little bit of a summary here, but it's actually 68 days from when we started testing to when we got back out here and did this. It was a total of 13 helicopter drops, 23 drops from the crane, and a heck of a lot of design improvements along the way.
Look how gentle.
I know.
Oh my goodness, like
It's like a balloon floating
it's
down.
gonna kiss the ground. Mwah.
Oh,
Thank you.
That was a precision land, right? You couldn't
Yeah.
see the target, but that was in the 5 meters.
It was incredible. And when we go and we like collect all the onboard data and then we run it through our simulation tools, we're able to see it continuously updating its route and how well it's sticking to it. We're staying within 15 to 20 meters along the entire path that's being planned. Like, this is incredible. And this is something that a team of 5 or 6 engineers put together over a course of 6 months. And so our next stops, we're going to go and continue next week and do more precision landings. Once we get 5 or 6 under our belt, we're going to feel real comfortable that this is a repeatable process. We're going to head down to Tucson and get taken up on a weather balloon to 25 kilometers and repeat this. So I'm like happy to have the opportunity to share a little bit about what we're doing at Outpost, show what can be done with a really small dedicated engineering team. At the beginning of this program, I went and reached out to all the main players in this industry, went and talked to Airborne Systems, and told them what we were trying to do. And honestly, they kind of laughed in our face. They said, "We tried that, it can't be done." And I'm just so proud of the work that our team has done here with a very small team. I'm looking forward to showing them this video and showing them that it can be done. All right.